Thanks very much, Ayan, for the introduction, and thank you all for coming. Thanks for organizing this very nice workshop. Many of the talks that I was able to attend have been very interesting. As always, it's a shame that we're not there in person, but well, what can we do? So the title of my talk today is The Complex Structure of Classical Hydrodynamics. And I want to talk about three different aspects of this that I have been interested in lately. The first is convergence of hydrodynamics. The second one is this issue of connecting hydrodynamics and transport to quantum chaos, the underlying mess of whatever is going on and some kind of quantum matter. And the third one is about bounds. This is the most recent work of mine. And I want to sort of connect this into kind of one picture of essentially looking at complex structure of classical hydrodynamics. So the motivation for this kind of thing that sort of fits more nicely into the scope of this particular workshop is to, of course, we all like to think about heavy ion collisions. We like to think about quark-gluon plasma, whether we're doing it for phenomenological reasons or experimental reasons, or because it provides this beautiful testing ground for strongly coupled dynamics and hydrodynamics. I mean, it's just, we come from different fields, from different environments, but we're all kind of interested in roughly the same questions. So some of these statements or, things that are motivating the talk today that have been appearing, in literature and have been discussed a lot, I put them sort of in little circles or ellipses. Some of these things that we like to discuss. For example, one question is, why does hydrodynamics work so well? So for example, we hear this a lot, hydrodynamics works extremely well, even when, I don't know, pressure gradients are not necessarily small, but it works very well. So, this is one of the motivations for the kind of things that I'll discuss today. So a second thing that we hear a lot today, that we have heard a lot about in recent years was this statement that hydrodynamics is an asymptotic series. So, I want to make more comments about this. And I want to, for example, tell you why this statement put in this way is certainly wrong. And then I want to say, we also know that, for example, when heavy ion collisions occur, when something happens, there's a lot of quantum dynamics and, stuff is very messy. So clearly there's some kind of microscopic mess that happens inside and, it will lead to things like thermalization, hydrodynamization, and more in condensed matter literature, people usually associate the formation of this kind of stuff with some kind of quantum chaos. So a particular aspect of the strongly coupled dynamics that I've been interested in lately was definitely quantum chaos, and I want to tell you what sort of new insights we've learned from the point of view of connecting quantum chaos to hydrodynamics, in particular in holographic theories. And last part of the talk will be, this discussion of bounds. So, for example, we know that the holographic ADS-CFT calculation for eta over S works extremely well. It gives us, a value. It gives a very universal value that's true across various theories. So, for example, we would like to know if there's a bound, for example, in eta over S. I mean, is it 1 over 4 pi? Maybe it's something else. Maybe it's some number times 1 over 4 pi. Things like this. There's also been recently a discussion, again, that resurfaced of this bound on the speed of sound, that it might be bounded from above by the conformal value. And if it is so, then, for example, cores of neutron stars may contain pure quark matter and so on. So I want to tell you some of sort of my recent things that I learned about this, again, through using complex analysis, sort of providing new sets of methods that give exact rigorous bounds given some analytic conditions of transport. And that will be the last part of the talk. Okay, so roughly I will give you some very brief introduction to hydrodynamics. This isn't really necessary. I will also say a few words about holographic duality. This may be slightly more necessary, but not really. I will only be using holographic duality, ADS-CFT in some cases. I will tell you which statements are general, which statements need ADS-CFT, but they will mostly be used to give you examples of the kind of stuff that I'm talking about. And you won't need any of the details of how this is actually computed. They will just be presented as examples. And then I will talk about these three different aspects. First, about convergence of hydrodynamics. through this language of complex spectral curves. Then I will talk about how we recently learned about what is the actual precise connection between transport and quantum chaos, which we know is only, which we know is true in holographic theories. So there will be a restriction to holography there. For example, this part of the talk, we simply have no understanding outside of holography. It may be true, it may not be true, we just don't know. And the last part will be again general, that won't need any holography, and it will be a derivation of rigorous bounds given some analytic conditions that the quantum field theory should obey. Okay, and then I'll give you some future directions. Okay, so let's start. So as I said, I mean, there isn't really any particular need for me to introduce hydrodynamics. You should, as always, think of hydrodynamics as some low energy limit, an effective theory, and we now know how to describe this effective field theory in terms of the Schwinger-Keldysh formalism. This has been developed now very nicely. It's a functional language that we can use, but for most of what I'll say today, this will not be necessary. So it's enough today to just think of hydrodynamics as a theory that expresses the dynamics of globally conserved operators. Each global continuous symmetry has an associated Noether current, and its zero divergence gives us the equations of motion. So for example, in a relativistic theory, we have conserved T mu nu, energy momentum tensor. We can also have charges. For example, some U1 Noether charge will give us this kind of an equation of motion. And if we have, say, this was presented in the previous talk by Yuji, for example, we showed that in electrodynamics, in a plasma, there's a higher form symmetry, which gives rise to a two-form current. So we can also have conservation laws of antisymmetric higher form tensors that can furnish equations of motion. These are word identities. Okay, so this is hydrodynamics. And what we do then is we take these tensors and we gradient expand them. This is also well known. We have zeroth order hydrodynamics, first order hydrodynamics with some unknown coefficients like shear viscosity, bulk viscosity, and so on, BRSSS theory, and so on. So the key assumption here is that, of course, if we're going to use gradient expansion, then the gradients should be small. How small? It's unclear, but they should be small. Otherwise, it's kind of strange to expect that hydrodynamics should work. Okay, so for a lot of my talk today, I will focus on specific observables, which are the modes. So the quasi-normal mode dispersion relations, which we derive in the following way. So we take our fields in which we expanded the theory, the velocity field, the temperature field, whatever other field you want to introduce. We Fourier decompose them with e to the minus I omega t plus I q dot x. Q is a vector momentum. And then, we basically plug this whole thing into the energy momentum tensor, plug this into the conservation laws, we expand out and we solve. So we solve for omega, the frequency, as a function of q, momentum. Q here, when I write it just like that, means the absolute value of the vector momentum. And this, let's say, compared to the equilibrium temperature, should be small. Again, this is equivalent to saying somehow that derivative should be small, right? So we know if we go to just neutral standard hydrodynamics, we'll have two types of modes. We'll have shear modes, which exhibit diffusion. So diffusion is characterized by a dispersion relation, which is omega equals to minus I times d q squared. Of course, d is the diffusion constant, which is computed in terms of the viscosity and energy density and pressure. And these, need to be supplied from a microscopic theory. You don't know what they are, and hydrodynamics doesn't tell you what they are unless you know how to compute them from QCD or QED or holography, whatever, for n equals to 4 super Young Mills, your favorite theory. Okay, but the structure can be determined just purely from this effective theory of hydrodynamics. Anyway, so the point is that d, the diffusion constant, is real, and the whole dispersion relation is purely imaginary. That means that it's purely dissipative, it's exponentially decaying. These modes are exponentially decaying. For longitudinal perturbations, we have a different type of a dispersion relation. It starts with a linear term in Q and continues with a quadratic term. So the first part is real, it comes with plus minus, and the unknown coefficient is the speed of sound. The first term coefficient is the attenuation coefficient, and again, it's imaginary. Okay, so first part is real, the second part is imaginary. All right, so let's say that we were able to complete this series for the energy momentum tensor, and we wrote the whole infinite series down, all right? This would look schematically like something like this, you know, at each term you have some number of tensors that you can write down. You know, each of these terms at each order in the derivative has an unknown coefficient, which we call the transport coefficient. But you know, let's say that you can write this down, then you would have this, you would plug this into the conservation of energy momentum tensor, you would decompose your fields in terms of Fourier modes, and you would again compute the dispersion relation. So now the dispersion relation, omega as a function of Q, is going to be an infinite series, okay? It's an infinite power series in Q to higher and higher powers with unknown coefficients in front, which you can compute from hydrodynamics, but their actual values will again depend on the microscopic content. So in my title, I said that this was classical hydrodynamics. This whole thing is a classical hydrodynamic series because we know that once one starts to include, you know, stochastic corrections or quantum corrections, whatever, we will find these non-analyticities in the theory, which go by the name of long time tails. So I will completely neglect these today. In the examples that I'll discuss, which will be holographic examples, which correspond to SUN, you know, gauge theories with n being large, these things are negligible because all these corrections are suppressed by 1 over nc squared at least. So, you know, they will be okay for those examples, but in general, for general theory of hydrodynamics, you should be aware that there's this caveat. And I think it's not unfair to say that we don't really understand, you know, there's a lot we don't understand about these long time tails, how exactly they behave at higher orders, what exactly are the full complex analytic properties and things like this. I think these are all great, interesting questions. I will tell you nothing about this today. All right. So for parts of what I'll discuss today, I will talk about conformal field theories because ADS-CFT is useful for conformal field theories, but in general, this doesn't need to be a specific restriction to most of what I'll say today. If there's conformal symmetry, then we know that this hydrodynamic series is constrained because T mu nu has to satisfy some conditions, like the fact that the trace must be 0 and that each term must transform in a locally Weyl covariant way. So you know, this imposes some restrictions on the type of terms that we can write down. So, okay, so what is actually the state of the art of this classification? Well, the situation is also not really great. So we know at first order that we can write down 2 terms. Those are the shear and bulk viscosity terms, and this is, you know, known as Navier-Stokes hydrodynamics. Then at the next order, we know how to write this down, but not for very long. This is now known as BRSSS theory. So we know that in a conformal theory, there are 5 additional coefficients. We also now more or less know how to go to the next term, but you know, there's perhaps still some discussion as to what is really the optimal number of terms that you can write at third order. Beyond third order, we know nothing. Okay, so you know, this number of terms that we write down somehow grows, but we do not know what is even the order of magnitude of the terms beyond third order. So it grows somehow, but for example, this is not completely clear, okay? But in general, there will be more and more and more terms, and they will all somehow contribute to this dispersion relation that I will consider. So as a second part of the introduction, I want to say that for parts of what I'll be saying, I'll be using holographic duality, which is a result of string theory that told us that some strongly coupled quantum field theories have a dual classical gravitational description. Classical when we have a quantum field theory and the large n limit, okay? So you don't need to know anything about the details of holography, ADS or ADS-CFT or gauge gravity duality, however you want to call it, except that there is a tool whereby we can actually compute these coefficients in some specific strongly coupled quantum field theories. And this is very useful because holography gives us, you know, essentially toy models of strongly interacting quantum field theories that we can solve. They're much easier to solve than QCD. So, you know, much easier to solve than QED or almost anything. So, you know, we can, you know, use them as well-defined unitary quantum field theories in order to learn about generic properties of transport that may exist in strongly coupled quantum field theories. Of course, we don't know what is the dual to QCD, but we have some very nice models. And you know, the simplest model that we understand very well is this n equals to 4 maximally supersymmetric Young-Mills theory with SUN gauge group and sub-Hooft coupling. And we normally take both of these to be large, n to be large and the coupling constant to be extremely large. And then this holographic duality becomes very simple. All right, so what holography is, it's a very useful tool for studying spectra, okay? We have a direct access to spectra of composite operators by performing some calculations that come from gravity, basically from black holes. So I want to just, when I say spectra, you know, I want to just start with something very, very simple. What I mean by a spectrum is the physical excitations of the theory. So if you take, let's say, a free, you know, zero coupling massive relativistic theory, and you look at what is the spectrum of this theory, all right, you know that there's the Einstein relation, which gives you energy in terms of momentum, right? E is m squared plus p squared, right? With everything set to 1, c set to 1, h bar set to 1. And now I can solve for this, right? I can solve for omega as a function of my wave vector, which I will call momentum. You know how this goes. So I can solve this. And of course, I get two solutions. There's omega equals to plus minus square root of m squared plus q squared, okay? It's purely real. There's no damping. And I can plot this, the positions of physical excitations in the complex frequency plane. So this means, you know, I fix my mass and I draw the complex plane and I draw these two excitations, these dots, where they lie in the complex frequency plane. So, you know, these are the poles of the associated correlation function. For example, if I were to compute the propagator for this theory, right, the 2-point function of phi, then you know that I would find p squared plus m squared in the denominator. And, you know, so by looking for poles of the correlation functions, I can find the places where the theory has physical excitations. So holography does just that. It gives you some kind of a working tool, essentially, to compute in, you know, among many other things, one can compute the physical excitations of the theory by, for example, looking at the ring down frequencies of the dual 5-dimensional black hole. So typically, we compute these spectra, for example, for conserved composite operators like the energy momentum tensor. And, you know, now I will do things at finite temperature. So I will fix my temperature. There's no mass like there was before. There's just a temperature scale in the theory. It's a CFT at finite temperature. So, you know, I find the poles of the correlation function, and they, you know, in some example, they will look like this. There's the thing that looks like a Christmas tree. So they are all purely relaxing, for example. Okay, this is a finite temperature system, so somehow it relaxes towards thermal equilibrium. Okay, so all right, and the positions of these dots, again, in the complex frequency plane, are the places where the correlation function, which equals schematically to b over a, has a equal to 0. Okay, great. Now, what do we know about, you know, what can we actually compute from holography? Well, for the simplest case of n equals to 4 super 9 mils at infinite coupling and infinite n, we can compute the dispersion relations analytically to this order. So this was done in this paper in 2019. So for sound modes, we're capable of computing these coefficients up to q to the 4th term. And for shear, we're capable of computing them up to the q to the 8th term, okay? Now, we cannot go further because of some troubles with analytic determination of the integrals that come into play and various functions. I mean, okay, one can in principle write some recursive equation, but they're very difficult to integrate explicitly. Okay, maybe if we tried harder, we could have done more, but this is the state of the art. This is as much as we know about these coefficients, all right? But as I said, the important thing is that this series will indefinitely continue up to infinity, okay? So the rest of the talk, I want to talk about these series. What can we say about these series? Do they converge? Do they diverge? What's their properties? And can we learn something from them? Are they constrained in some way? You know, what can we say about the coefficients and so on? Okay, so this will be the rest of the talk. Where crucially, you know, we're sort of used to treating frequency as a complex parameter. We will need to complexify both frequency and momentum, and you will see how this works. So let's start with number 1 and discuss, you know, a little bit of mathematics. Let's talk about complex spectral curves and what they have to say about convergence of this series. So what are complex spectral curves? Well, we know in the field of algebraic geometry, right, we have these algebraic curves, which are essentially solutions to polynomial equations of this form. You have some polynomial of 2 variables, x and y, and it has to be equal to 0, and you look for a solution y of x. Okay. That's what you're doing. So examples of such well-studied and completely classified things are, let's say, elliptic curves, okay? Where x and y are treated as real, and a, b constants are treated as integers. And this is, for example, y as a function of x catalog of these algebraic curves. Sometimes there are these little islands that they make, sometimes they're connected. And in certain cases, they are singular, okay? They have, for example, cusps or self-intersections. Bad things can happen to them. And those are called critical points. And those will be precisely the kind of things that I'll be interested in today. So, basically cusps and critical points of something that is a sort of a generalization of these algebraic curves. Okay, so what I'll be interested in today is solving exactly this kind of an equation, P of x and y equal to 0 for y as a function of x, but now where x and y are both complexified. So we're working in a C2 space, and basically this is why they're called complex spectral curves, okay? Complex curves. That's the sort of the terminology. All right, so of course, in general, it's very, very hard to solve this, right? You have some enormous polynomial to the 18th degree, or maybe you don't even have a polynomial. Finding an exact solution is essentially impossible. So what we do is we focus at a point and we look for local analysis around this point. So we know that typically local analysis will give you a series around the point, which will be a Taylor series, okay? So Taylor series is an expansion in, let's say, x to the n, right? In integer powers of n around the point. So there's a generalization of these Taylor series, which was figured out by, I don't know, 19th century, maybe already by Newton a little bit. And these things are called Puiseux series. And Puiseux series are series in fractional powers of the expansion coefficient. So let me give you a simple example. Let's take essentially an equation for a circle. So x squared plus y squared equals to 1, but let's complexify both x and y, okay? Of course, we know how to find a solution, but let's not do this. Let's just look at local analysis. So let's find a regular point. So a regular point is a place where, of course, the p is solved, so it equals to 0 at some point. And it also must be true that the first derivative with respect to y, so I'm solving for y of x, so the first derivative with respect to y must be non-zero. If this is true, then then by the implicit function theorem and all these associated theorems, you can find the Taylor series around this point. So there's an example of such a point. It's 0, 1, and one finds a Taylor series in x. It comes with x to the 0, x squared, x to the 4th. It could have come with x to the 7, whatever. It comes in integer powers. Now, we can also look for a critical point of higher order. So what this means is that, of course, P is solved at the point, and now the first derivative is still 0. So you cannot use the implicit function theorem. So, it's still 0, but let's say that only the second derivative is 0, okay? This is called the critical point of order 2. There are two such points here, and they're plus minus 1, 0. So then these theorems, in particular the Puiseux theorem, say that now there is an analytic series that you can expand around this point, but there are two branches of such a series around each point because the critical point is of order 2. And moreover, the series is expanded in terms of a fractional power. In particular, because it's order 2, it's expanded in powers of a half, okay? So if we focus on the point 1, 0, there are two branches of Puiseux series around such point. And they go, as you can see, in x minus 1 to a half, then to 3 halves, 5 halves, and so on, okay? The theorem also tells you that such a series is convergent. It's convergent, it's analytic in the sense of Puiseux around the point, and it has a finite radius of convergence, which is determined by the next critical point. So it's convergent always until something bad happens to this curve, okay? So basically, you can find all the critical points, expand around one of them, and then you are guaranteed that the series will be convergent up to the next critical point where there's this cusp singularity or something bad happens again to the curve. So the radius of convergence for these two examples, in the first case, it's 1, in the second case, it's 2, okay? And you can see this immediately because the distance is 2 to the next point, okay? From 1 to plus 1 is 2. All right, great. So what does this have to do with hydrodynamics? So when we solve for hydrodynamic dispersion relations, we're essentially solving exactly the same problem, right? Either from holography, we have a quasi-normal mode equation, or we have some we're computing a determinant of the linearized operator, it doesn't matter. We're solving some equation P of Q squared and omega equals to 0, and we're looking for a solution omega as a function of Q squared. It's important, essential, that this is Q squared because Q is a vector. So the only parameter that can be a scalar is Q squared, okay? And I will be complexifying both of them and normalizing them with respect to temperature in this way. So if we just look at first order hydrodynamics, I can show you the simplest example of such a curve. So P is called the spectral curve. You can see that you get an obvious part here to which the solution is diffusion, and another obvious part here to which the solution is sound. So because this is in 3+1 dimensions, we have basically the diffusive part and the sound part factorize. So each one of them separately has to be 0, and the diffusive part is squared because we have a remaining SO2 symmetry, so we can have 2 diffusive modes. This is why there's a square here. All right, so this spectral curve has a regular point. It has a point where one can solve, find it to be 0, and the first derivative with respect to omega is non-zero. So there's a regular point. There's also a critical point of order 2, where P is 0, the first derivative is 0, and only the second derivative is non-zero, okay? So it turns out that the diffusive modes are regular points, are expansions of a regular point, whereas the sound modes are expansions of a P equals to 2 critical point. So one finds immediately that basically the diffusive dispersion relation will be a Taylor series in Q squared, because that's the only parameter that you're allowed to use, to the n. So of course, then if you go to 1 dimension, it looks like it's a series in Q squared, Q to the 4, Q to the 8, right? 6, 8, and so on. But it's a single series, and you can immediately also tell that every single term, just from these theorems, that every term will be purely imaginary, and that the coefficients, like these d's and every other coefficient will be real. So it tells you this, and it also tells you immediately that the radius of convergence will be finite. So for sound, the Puiseux theorem gives you, more interesting things. It tells you that there will have to be 2 branches because it's a critical point of P equals to 2. So this fact that we have plus minus from the mathematics point of view comes out from the fact that P equals to 2. It also tells you how they will have to alternate these plus minus signs. This is fixed by the theorem. And it tells you, because P is 2, is that it will be a series in momentum vector squared to the power of n over 2. Okay? So basically, the entire series is constrained by the theorem. And it tells you again that the radius of convergence will be finite, determined by the next critical point. All right, so now one can, so this is a general statement, and it's nice to to see how this, for example, works in a specific case. So we can go to holography, look at n equals to 4 super Young Mills, and see what this actually means, right? So we've determined that the hydrodynamic series will be convergent, and it will have a radius of convergence up to the next critical point. So the question is, where is this next critical point? What will it look like? All right. So we go to n equals to 4 super Young Mills, and we compute the spectrum in the following way. I'm going to fix the temperature of my theory, and then I am going to slowly vary my momentum and plot the spectrum in the complex frequency plane. So this is the complex frequency plane. This is the usual Christmas tree that we know, and this is the diffusive mode. Okay, we're doing this for diffusion. And what I'm going to do now is I'm going to complexify my momentum squared. So I'm going to write it as this. There's going to be the magnitude of momentum squared that I'm going to fix to a number, in this case 1. And then I'm going to vary the phase from 0 to 2 pi, okay? So what you can see is that, when you vary the phase, this happens. All right, it's not, nothing spectacular. Basically, you start with standard hydrodynamic modes at real momentum. You complexify it and you vary it, and they make a little circle. Very nice. That's it. Now you increase the absolute value of your momentum. What they start doing is much more interesting. So they start, behaving like some kind of planetary motions. These singularities attract and repel, and they do various things. And you can see here. So the diffusive mode here will come very, very close to one of the gapped modes, but not quite. They're still repelling, okay? Then we increase even further, and they come even closer. So eventually they collide. So basically, the collision of the hydrodynamic mode with one of the gapped modes in the spectrum, one of the massive modes in the spectrum, somewhere in the complexified space of momentum and frequency is the next critical point. And because two of them collide, you already know that this will be a P equals to 2 critical point. And again, Puisol can tell you a lot about this collision. All right, so what happens when you increase this even further, right? If you increase the absolute value of momentum even further, is basically what you get is the equivalent of the quantum mechanical level crossing phenomenon. What you get is this. So basically, what you can see here, okay, fine. So this is the diffusive mode. This is the gapped mode, one of the massive modes, whatever. You can call it a meson or whatever you want. It's some composite massive mode in the spectrum of energy. This is, this is transverse momentum, but whatever. So, you vary the phase, they come together, and actually now at this point, they cross levels. So the hydrodynamic mode becomes the massive mode, and as you vary the phase by 2 pi, it's the hydrodynamic mode that returns to the position of where the gapped mode started. So basically, this pair of gapped mode and the hydrodynamic mode, they merge into one thing. They become one curve. And you can continue, and this happens more and more. And basically what you find is that all of the excitations in the spectrum are a part of one complex curve. So they all know about each other, essentially. Each one of them knows everything about the other ones. So this is just basically the same plot. I already showed you these diffusive poles. So the same thing happens for sound mode, but it's more complicated. So the statement that I want to make here is that the dispersion relations are always convergent. They have a finite radius of convergence, and the radius of convergence is determined by the collision with the mode, with the massive mode somewhere in the spectrum, okay? And of course, the radius of convergence is going to then be the minimal absolute value of momentum where such a collision occurs. So we can compute them. For shear, we can compute in n equals to 4 super Young-Mills theory numerically. This is the value. For sound, we can actually get it analytically for some reason. We don't know why, but it's very simple. Okay, so you can, as I said, you can continue, and all these modes in the spectrum, they play a very nice dance, and they exchange places and so on. And essentially, they know about each other. Okay, so in principle, each one of them is reconstructible from another one through this sequence of collisions and Puisol theorems. Okay, so the important thing is that basically, if we go now to the to draw the complex structure of frequency as a function of momentum, each collision is going to give you a branch cut in the dispersion relation. So you should really think of all these dispersion relations for each of the mode in the spectrum as different sheets of the Riemann surface after the, let's say, hydrodynamic dispersion relation is analytically continued, right? So this means, so you have the hydrodynamic dispersion relation, it converges in some circle, but you can perform a unique analytic continuation, and then different sheets of the Riemann surface around these branch cuts are different modes in the spectrum, okay? That's the kind of a picture that emerges. So in order to make some contact, for example, what is kind of interesting about this is that it says something about this unreasonable effectiveness. It says something about, for example, why hydrodynamics may work for large derivatives. In particular, so I said that this is convergent. So if you actually compute so it's convergent in general in n equals to 4 super Young-Mills and other holographic theories, you can actually compute the value for the radius of convergence. And it comes out to be very large. It's, of the order of some number times the Matsubara frequency. So actually it's around, Q over T of order 10, which is, naively, I would have expected that in order to have good gradient expansion, Q over T should be very small. But actually, it turns out that it converges, the Hydro series converges up to Q over T of order 10, okay? So one statement that I can make is that hydrodynamics as a theory, one cannot say that the theory is convergent or asymptotic. It depends on the observable. So we know that in momentum space, dispersion relations are convergent. Now, if we go to position space, then it depends. In some cases, they're divergent. In some cases, they're convergent. So, for example, and this is just the property of Fourier transform and also of the initial conditions that you use in order to evolve in position space. So, of course, we know from previous works that it's true that, for Bjork and flow and these kinds of things, the hydro series is divergent. That's fine. It's not because hydrodynamics is by itself a divergent theory. It's because it's because in position space, Bjork and flow has the kind of property, for example, that there's an essential singularity at infinity. So this imposes the fact that it will be a divergent series. But for example, as was shown recently in a paper by Heller, Spalinsky, and other people I will quote it at the end, if, for example, even in position space, the support of these functions is finite, then the hydrodynamics can also be convergent in position space. So one has to be careful about such statements, okay? So now let me move on to the second discussion of this, hydrodynamics and quantum chaos. So, all right, so we know, we're changing gears slightly. What do we know about chaos? So we know that classical chaos is essentially, extreme sensitivity to initial conditions, right? You have some particles, they're flying around, and they will diverge exponentially, and to this we associate to this divergence we associate the Lyapunov exponent and the butterfly velocity of the linear front of this propagation of chaos. Okay. So a lot is known about classical chaos, not, a little less is known about quantum chaos, or maybe a lot less. But what we do know is that certainly these molecules or whatever, protons, neutrons, quarks, gluons, whatever, they collide chaotically after an experiment, okay? So in recent years, there's been a resurgence of interest in quantum chaos, in particular because people found or refound an observable that's very useful to compute, and it's a quantum observable. It's an out-of-time ordered correlation function, has funny properties, but it does exhibit exponential growth. And one can call the exponents of this exponential growth in analogy with chaos by Lyapunov exponent and the butterfly velocity. Okay, so all right, so there's some kind of chaotic mess. It builds up, and eventually we know that the system thermalizes, right? So this kind of mess gives rise to hydrodynamics. The question is how. Okay, and this is not a resolved question in quantum mechanics or in quantum field theory at all. Okay, so this is why it's a very interesting, messy, many-body question that is of interest to condensed matter and to heavy ion phenomenology and all sorts of things. So the standard lore in renormalization group language is, of course, that microscopic physics, like quantum chaos, is somehow washed out, and we have at long time scales some kind of hydrodynamics. It's emergent, but we cannot reconstruct, the mass of the quark by measuring viscosity of water. Okay, this is what renormalization group tells us. So it turns out that in these holographic theories, one can actually do something like this. Okay, so there was recently this very beautiful result that came from work of Maldacena, Schenker, and Stanford, who showed that basically this Lyapunov exponent that you can compute from OTOC. OTOC is this out-of-time ordered correlation function, whatever. If you don't know what it is, it doesn't matter. It's some correlation function. We believe it diagnoses chaos. One can prove an upper bound on this quantity, and it's bounded from above by 2 pi times the temperature. Again, this famous Matsubara thing. This is a proof that comes out of some analyticity assumptions on this 4-point function, and it's very reasonable, and we believe that this is probably correct. Okay. It's probably the nicest, cleanest bound that we have in nature. So one can also sort of prove something very similar for systems that don't have exponential chaos. We prove this for spin chains, but this I will not discuss today. So the question is now, out of all this chaos, how does hydrodynamics emerge? Okay, so there's been a lot of discussion regarding how, for example, the diffusion constant is related to the quantities that characterize chaos, like the butterfly velocity VB and the Lyapunov exponent. So at least for holographic theories, for any theory that has a holographic dual, we have now resolved this question. And the answer to how this works is called now pole skipping. So we found this first in this paper, then there was this paper, which was able to show that this exists in some effective theories. Then some combination of us proved that this was true generically in gravity, and we were able to find why exactly this works from a horizon kind of an analysis. And then I also showed that this is true in theories with higher derivative corrections, so finite coupling corrections and so on. So we believe that this is true in all holographic theories. And now it's been also shown to be true in some CFTs, which may not have a very obvious holographic dual and so on. Anyway, the statement that we now understand is the following. So let's take this dispersion relation, right? I've talked about it a lot. It converges, all right? I can resum it and I can analytically extend this thing. So it's going to be some function. Omega is a function of Q. So for all theories that have a holographic dual, the following thing happens. So this dispersion relation for sound, let's focus on sound. If I take my momentum and I analytically continue it to be imaginary, at some value of I times Q0, it will equal to I times the Lyapunov exponent, okay? So in all these holographic theories, of course, the Lyapunov exponent is 2 pi t. It's maximal, so this is not very spectacular. However, this will happen at one precise Q, at one momentum, which will know about the butterfly velocity, okay? So at this point, Q will be equal to lambda, the Lyapunov exponent, over the butterfly velocity. Fine. So this point is where this point happens in the analytically continued space of momentum. It's determined by what is called pole skipping. So if you compute the associated correlation function, right? Let's say energy-energy correlator, which we know will have the pole, which is the sound mode. Then, of course, at the pole, at the mode, the pole will be equal to 0. But what also happens at this number of special points in complexified space is that also the numerator goes to 0. So essentially at these special points, the correlation function is undetermined. It's 0 over 0. And this is why we call this pole skipping. So you can see some very simple example of some theory, something like this can happen. There's a pole which looks diffusive, minus I omega plus dq squared. It's a 0. But this happens, the numerator is also 0 when omega is given by the Lyapunov exponent. So this generically happens in every single quantum field theory that has a holographic dual. I should say actually that people didn't usually say this in these terms, but hydrodynamics itself around omega equals to 0, Q equals to 0 is an example of such a pole skipping thing. When we say that Kubo formulae, for example, that the limit of Q to 0, omega to 0 does not commute, it's kind of the same statement, that there's an indeterminacy, right, in the correlation function. So there are many questions associated. Maybe these are special points for effective theories and so on. We don't know. Anyway, but this is true generically, and we can compute these basically properties of quantum chaos by just finding a special point in the energy-energy correlator, right? You don't have to go and diagnose 4-point functions of generic single trace operators that are, some high dimension operators in QFT. You can just compute the energy-energy correlator and only a 2-point function and find places of 0 over 0. And the lowest one will tell you what is the butterfly velocity of the quantum chaotic spread, okay? And this chaotic point can be either inside of the radius of convergence or outside. And you can, if it's outside, you can access it by analytic continuation of the dispersion relation. So in gravity, there's a special reason for this. We understand it. There's a special new property of Einstein's equations, which I will not discuss. What is fascinating is that from the point of view of QFT, we have essentially zero understanding why this is happening. What is even the meaning of 0 over 0, okay? So from the point of view of hydrodynamics, what this does is the following. It constrains the motion of the dispersion relation through a predetermined point. Basically, chaos does something, and it says that every single hydrodynamic dispersion relation, no matter how many chemical potentials you have, how complicated it is, if you have baryon number, whatever, it will have to go through a predetermined point that's determined by chaos, and it's this special pole skipping point, okay? So this whole resummation is pre-constrained to go through one point. It's some kind of infinite, I don't know what, focusing theorem for no matter what the theory is. So this is an example for diffusion, for sound, they all go through these predetermined points, okay? So we now actually know that in all of these quantum field theories, each correlator actually has an infinite number of such 0/0 points. So it's an extremely generic thing. We do not know what is the meaning of them. We only know that the lowest one, that has the lowest frequency, knows about quantum chaos. Okay, the other ones, it's unclear. All right, but they do have some kind of special purpose in quantum field theory, and it remains to be discovered what exactly this means from the pure point of view of QFT. What is the meaning of 0/0? Okay. All right. So how much more time do I have to talk about briefly about the last?
Maybe you can take 3 to 4 more minutes so that we have also time for questions.
Okay. Right. Then they're bounds. So then I will just briefly say what is the idea. So given that we have, such a beautiful bound, an upper bound on the Lyapunov exponent, I was then interested in whether one can invent or discover other analytic properties of dispersion relations that will give me rigorous bounds on the coefficients of the dispersion relations, okay? Because, these bounds have been discussed for a very long time. So I was trying to find some, new analytic structure that can give us something. So it turns out that one can do this. And I will not have time to go into the details. What I told you so far is that the dispersion relations are analytic, okay, in some region. They know about quantum chaos. Then there's an extra structure which one can find in these dispersion relations. And essentially, it's called univalence. So what this means is that the functions are analytic, but they're also injective, okay? So if for those of you who don't remember what a function being injective means, it just means that f of z1 is not equal to f of z2 for all z1 not equal to z2, okay? So you can find that these dispersion relations do have this property of injectivity in some region of the complex space. So it turns out that this is actually enough. As long as you find such a region, it's enough to put rigorous bounds on every single coefficient of the dispersion relation. There's a lot of mathematical machinery that's been discovered, by other people. It goes under the name of univalent functions. But what happens is, we know that complex analytics, this is called holomorphic functions, are very stiff. So if they're injective, they're even stiffer, okay? And one can prove something called the growth theorem, which tells you how such a function can grow at most at every point where it's injective. And moreover, when you have a series, if you normalize the series in such a way that the first coefficient is 1, and then each coefficient, like in the hydrodynamic series, is some number, let's call it Bn. There's a very famous statement actually called the Bieberbach conjecture, which was proven by a French mathematician, Desbranches. And he proved that each coefficient is bounded from above by an integer, okay? So this series can, after some rescaling and reshuffling around, can at most be 1 plus 2 times zeta squared plus 3 times zeta cubed and so on, okay? So you can actually use this to put a bound on every single coefficient of the hydrodynamic series, including diffusion constant and the speed of sound, okay? So all you need is to find some region in this complex space where the function is injective, all right? Then you can, for any region, from the Riemann mapping theorem that you can map it to a disk by conformal transformation. So all you need to know then is the value of your dispersion relation at one point. Like, for example, the pole skipping point, which is very easy to compute. And this is enough to put actually upper and lower bounds on every single term in the hydrodynamic dispersion relation. So I don't have time to go into details, but for example, you can bound diffusion, you can bound every single other coefficient, you can bound speed of sound. And this is some example to show that, this univalence is really satisfied in, for example, in holographic theories. The idea, so, it's kind of a new set of tools that allows you to put bounds given some more analytic, complex information about your hydrodynamics. All right, so basically, I want to just finish with this little statement. So, for example, what you can do with this. So you can find many different bounds given properties of pole skipping. That's quite easy to do. What you can also do is find a necessary condition of what your theory should satisfy in order, for example, to give you a conformal bound on the speed of sound. So you can, so all that has to happen is that you have to have some, say you have some set of quantum field theories, they have some dispersion relations for sound, okay, in this, n set of quantum field theories. If all of those quantum field theories allow a conformal map of this region of injectivity of the dispersion relation to a disk that satisfies one particular very simple property, then you can prove that the speed of sound will be bounded from above, okay? And basically, these tools give you insight into what kind of a necessary condition your dispersion relation has to satisfy in order to find specific bounds for every single coefficient of the hydrodynamic series. So just to conclude, I guess I showed you today that, by taking this complex analysis and complex analytic structures more seriously, one can find new generic properties of transport, of what they should satisfy. So for example, one thing I showed you and claimed was that dispersion relations always converge in momentum space, whereas it, in position space, because of properties of Fourier transform, sometimes they converge, sometimes they don't. It depends. But one cannot in general claim that hydrodynamics is a divergent theory. It's not, it's not like perturbation theory. But I guess also even there, you can't really claim anything in general. Anyway, so yeah, so there's a subtlety as opposed, with regard to what observable you're looking at. And you might ask what happens in chiral effective theories and things like this, which are also gradient expansions. Then I showed you, this new connection between hydrodynamics and quantum chaos. The question there is, what is the meaning of these 0 over zeros in correlation functions in QFT? And is there, a generalization of all this to, I don't know, QCD? Is there some kind of pole skipping there? We have no idea. Another, I think, conceptual question to which I thought about, but I don't know the answer, is whether people have actually discussed quantum chaos in the context of heavy ion collisions. I don't know, do people discuss quantum chaos after the collision in the quark-gluon plasma, the mess, that happens? It's probably chaotic. I mean, why would it not be? I don't know, actually. Maybe some people in the audience know about this. And lastly, I didn't have much time to go into this, but I briefly told you that there's a new set of now methods that come from complex analysis, which allow for rigorous derivations of lower and upper bounds on diffusion, on the speed of sound, and all of the other hydrodynamic coefficients at higher orders. And it will be interesting actually to test this, to see, do the theories that we know fit into the necessary classes that may lead to, I don't know, the KSS bound or the conformal speed of sound bound and things like this. And I have to caution, of course, at the end, is that you must not forget that all of these things were said about classical hydrodynamics. So, as soon as we go to n equals to 3 or something like this, it's at present unclear how much of all this story will remain, because we have not really included the effects of long time tails into all this complex structure discussions. But we should, and we will, and this is as much as we know at the moment, and there's a lot to be done. Thank you very much for your attention.
Thanks, Saso, for this very beautiful and pedagogical talk. So we already have a question in the chat box from Paul. Maybe Paul can ask it himself.
No, sorry, I didn't see it. Yeah, if I saw it during the talk, I would have.
I think it's about the presence of nonlinearities in hydrodynamic expansion and its consequence for the convergence of derivative expansion, I think. So, but Paul can ask it himself, maybe.
Yeah, I'm happy to do that. So hi, this is Paul Romochke.
Hey.
I think I disagree with your statement that the convergence of hydrodynamics depends on sort of the Fourier transform or whatever. So basically, I think your statement was made on the dispersion relation that you calculated in holography. The dispersion relation is something that you calculate by linearizing in G. So basically, that means you're doing essentially linear hydrodynamics, right? I mean, there are some terms that just don't contribute to this dispersion relation, as you know well.
Of course, yeah.
In fact, you can probably convince yourselves that the number of terms at nth order in gradient is not n factorial. It's probably more like polynomial. So I would completely agree with you that the dispersion relation is always a convergent series, even though it's all orders in gradients. But basically what that means is that your statement is that linear hydrodynamics is a convergent series, to which I think I would agree. That does not mean that hydrodynamics, by which we usually mean a expansion that includes all sorts of possible non-linearities is also convergent. And I think this is precisely the reason why other people like Heller and company have found that the number of terms in Bjorken flow in n equals 4 superlinears goes n factorial as you go to order n in the expansion, and you get a divergent series. You just have many, many more terms that you can build out of a non-linear combination of gradients. Can you comment on this?
Yes, I can comment on this, yes. So when we wrote this paper about convergence, right, we made it very clear that this is a statement, as you say, about linearized hydrodynamics, about dispersion relations, right? So we do not have any disagreement. Linearized hydrodynamics in momentum space is convergent. Okay, good. Now the question is, what happens, first of all, in linearized hydrodynamics in position space and in nonlinear hydrodynamics in position space, right? So Bjorken flow is a solution to non-linearized equation. Right, so first of all, we can't really talk about momentum space in nonlinear theories, okay? That doesn't make any sense. So I would say, okay, so there was recently this paper that I sort of cited here, where they showed actually that even linearized hydrodynamics can be divergent in position space. So I would stand by my comment that this is a result of Fourier transform. So for example, we also put a little example in our discussion. You can just take a single particle dispersion relation, take 1 over m squared plus p squared and expand in p. This is a convergent series. The propagator is convergent. It's linearized. It couldn't be any more linear. It's a propagator. You can do a Fourier transform of this, and in position space, this is linearized theory, it will be divergent because there's an essential singularity at infinite time. So even in linearized hydrodynamics, in position space, you can have divergent series. And actually this paper made a claim that it depended on the support of the function of the initial condition. So basically in position space, you have two things. One is this microscopic stuff that is going on, like the coefficients, and this is seen by momentum space. This is convergent. Then you have to multiply this by the initial condition, and the initial condition for hydrodynamic evolution is going to be in some set of functions. Now in position space, it will depend what set of functions these initial conditions are in. So the result in position space in linearized hydrodynamics can also be either convergent or divergent, depending on how that works. So, okay, then there is the nonlinear hydrodynamics like Bjorken flow. There it's divergent, but so one of the options is, of course, what you mentioned. Yes, it's nonlinear, so there are more coefficients, but you don't really know how they add together, right? I mean, just because there are more terms doesn't mean that some of them don't cancel out. It's possible that any nonlinear theory will be divergent, but I very much doubt that. But we don't have a proof of that. Yeah. So I mean, maybe Paul, was it clear what I was trying to say, or I'm just babbling?
Yeah, I mean, I think it's clear what you wanted to say. I think we have no example of a nonlinear theory that's convergent. Is that a true statement?
I think we have an example. I think there was some papers by I think it was Georges Noronha that had something. I need to look this up, but I think we did have some example. But I cannot claim this with 100% certainty. So I sympathize with the worry that nonlinear hydrodynamics will have more terms, but I don't think that this is the reason for divergence. I think the reason for divergence in Bjorken flow is that it's a solution with essential singularity at infinite proper time. And as soon as that's the case, then it doesn't fit into the class of well-behaved functions, then it diverges. But it would be very important to better understand this, exactly what you said. You know, if we have n terms versus n factorial terms, yeah, I cannot make a precise statement about this, but I think, yeah, so what you raise is what we have thought about a lot, we have discussed it, but I cannot make a precise statement now. The only precise statement that I can make is that in momentum space, linearized hydrodynamics converges. In position space, linearized hydrodynamics either diverges or converges depending on the class of functions that the initial conditions fit in. That's the only precise thing I can say for now.
Okay, thanks.
Thank
the
you
next
for
question,
Mike.
Next question is from Mike about bound of sound in QCD. Maybe Mike can ask himself.
I think the answer is no. Sorry, Mike, go ahead.
Yeah, it's more
it would be nice to hear your voice at least.
I think I already know the answer, but it's to prompt a discussion, right? So, so you have this nice proof now in a certain, large class of theories that you have this bound. So I guess the next question is QCD in this class of theories?
That's right. Yeah.
We know from PQCD at least, which is a limited tool, that coming along the high temperature axis or the high density axis, that the speed of sound approaches approaches 1/3 from below, right? So, what's the next step if you were to try to apply this to actual QCD? I guess that's the question.
Yeah, I don't really know. I mean, so I think that there were some arguments about a large baryon chemical potential where it might violate. Do you know more about this?
There are some studies where you can have in an intermediate regime, people are claiming that you can have it violate the bound and go above 1/3, but then eventually it does have to come back down and approach from below. But
because you go to conformal theory.
Yes, eventually, yes.
Yeah. So I don't know. So I mean, honestly, I think the first step for me is to apply these conditions, see how, so basically what I would like to do is take some holographic model. All right, it's not satisfactory, but we're stupid. So let me take some holographic model where I know that this bound can be violated or obeyed. There are such models. And I want to see exactly how the cases that violate also violate this injectivity condition. Where does it go wrong? I think that would be the first case. Yeah, and then maybe I will learn something from there. I honestly don't know how to apply this to QCD yet, because I don't know how to test this analytic condition in QCD. I wish. I'm too limited for the moment to really make a claim about QCD, unfortunately.
Thanks.
Okay, so Derek has a question
now. Yes.
Yeah, so somehow I could ask it myself. I mean, so you said, what's the physical meaning of the pole skipping? So that's a strong question, but at least in the holography picture, you have a membrane paradigm understanding for the pole skipping. And I wondered if you could explain somehow that I consider physics too. Like, what is the physics of the membrane paradigm that happens when this pole skipping happens?
Right. So in gravity, what happens is the following. So so let's say you're solving linearized Einstein's equations to get a 2-point function. You're solving Einstein's equations, plus they can be coupled to any kind of matter you want. Fine, doesn't matter. So let's say you go to the horizon, okay? Yeah. And solve this horrible system of coupled equations by starting at the horizon and then perturbatively solving in distance inwards, okay? In some expansion of, let's say, r minus r horizon to the power n. All right. So, because this is a set of second-order differential equations, you will need 2 boundary conditions in order to solve this, okay? So this is so normally you impose infalling boundary conditions at the horizon, all right? So you've done one thing, then you can solve, let's say you solve all the way to the boundary, then you impose the Dirichlet boundary condition and you find the quasi-normal mode, fine. So it turns out that if you complexify frequency and momentum, at some isolated points of frequency and momentum, you cannot do this. So what happens concretely is that you lose one of the Einstein's equations. So at the horizon, one of these equations that you need in order to solve consistently is just identically zero. So you cannot solve for the coefficients of this expansion because you've lost an equation. So basically, at some values of frequency and momentum, and there's an infinite number of such points, you have a freedom of a constant function. You can add a constant function, and it is not, it's not constrained by any infalling or outgoing boundary condition. You simply cannot say if it's ingoing or outgoing because you've lost an equation. So what happens then? Fine, you start solving and you have a free function. Then by the time you get to the boundary, this means that you were unable to fix the ratio of numerator to the denominator. Okay, this B over A. So horizon will fix the ratio of B over A. And at some special points, you cannot fix this. So it can be anything. It's indeterminate. So you can pick anything at the boundary and find consistent solution all the way to the horizon. You can pick a pole, you can pick a zero. So both exist depending on the direction of how you approach that point. This is what happens. It's basically in the set of Einstein's equations at special points, at pole skipping points, one of them is identically zero. So you cannot set a boundary condition there. You have a free function. It doesn't matter what you pick, there's a free solution that you can just carry around. This is what happens from the point of view of gravity. And it's completely generic. I mean, this, because it's a horizon property, this has nothing to do with ADS either. I mean, this is still true in Minkowski space.
Right.
In Minkowski space,
all of this has the pole skipping point, that's not for, is Q complexified at that point? Yeah, right.
It depends on the channel. For example, so in the sound channel, for the lowest pole skipping point, it's purely imaginary. For example, for diffusion, it happens actually for real Q. So there's a pole skipping point for real momentum for diffusion. I had a plot here, for example, this is I don't know if you can still see my screen. So this is diffusion in n equals to 4. So it goes through this predetermined pole skipping point actually for real momentum for diffusion. Yeah, but then, for example, I didn't say much about this picture, but if you take some 2D CFT, which is dual to BTZ black hole, and you plot the spectrum in the complex omega plane, there's an infinite sequence, it looks like a tree, of points where there's an indeterminacy in the dual correlation function. So there are these black dots, this is where there's an indeterminacy. So it happens at some complex momentum, but it always happens at a multiple of Matsubara frequency, which is also weird because these are real-time correlators. This has nothing to do with Euclidean Matsubara frequencies, and yet still somehow these Matsubara frequencies are special. Yeah, and sometimes it even happens in the upper half plane for analytic continuation. Yeah, this is how it works. So if you have some idea what this means in QFT, I would be happy to hear. Paul. Okay. Paul wrote something.
Paul has a comment on he has an example where the conformal bound for speed of sound is violated in large N scalar field theory. He has a reference for that. So Paul wants to make some comment on that also.
I know this paper very well, but I didn't appreciate that this model actually violates the speed of sound thing. Okay, well that's nice.
There's no comment.
Yeah, there are examples.
Yeah, exactly. Is there still time, or should we move on? I have one more question if there's time.
Sure, please go ahead.
So this is a question concerning the pole skipping. Mm-hmm. If I understand correctly, the pole skipping of the sound channel, the T00 correlator channel, is the one that we associate with the Lyapunov exponent of quantum chaos.
Yes.
Is there any chance to figure out what the pole skipping in the other channels would correspond to, like the scalar channel or the shear channel? Do you have any comment?
So the only thing I know about this, the only thing we know is that in neutral theories, like for example, n equals to 4 super Young-Mills, so in neutral theories, like n equals to 4 super Young-Mills, there is also, so you can still figure out the pole skipping, you can still figure out the chaos point, the butterfly velocity, and the Lyapunov exponent from the lowest one, okay? Both in the shear channel and in the scalar channel. If you go to theories that are not neutral, like n equals to 4 super young mils, then it happens somewhere and we don't know what it means. Yeah, we don't, sorry, there was a cleaner came to my office. I don't know we don't know what it means. It happens at some momentum. It happens at the Matsubara frequency. It happens in some multiple of imaginary Matsubara frequency, but we don't know. I mean, maybe it would be helpful to see it from field theory. Yeah, we don't know what is the meaning of those momenta. If they have something to do with chaos or something else, it's I don't know. Yeah, it's also not entirely clear how to figure this out. So yeah, it's not like an obvious calculation you do and then I would know what it means. Yeah, but I've thought about this a lot. And I cannot answer, unfortunately, but it's a very important question. Yeah.
Okay, thank you.
Okay, so since we have only 2 more minutes before we move to the next talk, so I want to ask a short question. So it is, so we said that if you look into this different poles of in the Christmas tree, there will, and move them in the complex plane, there will be arbitrary number of points colliding somewhere, but I didn't, your kind of motion, the movie that you made didn't show that. It was only 2 poles colliding at most.
Yeah, the one I showed was the lowest, was the hydro modes colliding with the first gapped mode. Then I didn't much discuss this, but these are sort of higher pictures, so you can, I don't know if it's visible from any of these ones, but I mean, you know, after the first collision, then the hydro mode isn't really the hydro mode anymore. They're all 3 are connected together in some curve. After that, you know, you can continue, and then this mode will then collide with something else, with the next gapped mode, and so on. So, you know, there's some kind of successive sequence of these collisions.
As you increase your mod q square, you mean?
Yes. Yes.
I see. Okay.
Yeah. So
I see.
One nice thing about this is that, you know, so you know that your hydro series will converge up to the critical point. So if you were able to, you know, so then you also know that it's a collision of type 2. So then, you know, this is basically why at that point, then the gapped mode and the hydrodynamic mode become 2 different branches of the full complex curve. Yeah. And so, you know, they're all connected somehow.
I see.
Through these collisions. Yeah.
So one more short question would be that, normally in classical chaos, especially Hamiltonian, the sum of Lyapunov exponents is 0. And so actually you have a spectrum of Lyapunov exponents, right?
Yeah, for a conservative model, you have as many positive as you have negative.
Yeah. So since you have a spectrum, I mean, won't you expect, so is this like the spectrum comes from different operators here and there is no way to interpret the other ones, other poles, or it could be some higher order Lyapunov?
It's unclear. So probably in this, that's a very good question. So probably in this, I expect that in this theory with maximal chaos, there's only one Lyapunov exponent. When you go to non-maximal chaos, there's probably a continuum of Lyapunov exponents that depend on momentum. So I don't know what kind of pole skipping you can find there. I mean, there are people investigating actually this for the SYK chain going away from maximal chaos.
So there is a study of black holes from matrix models. What you actually see there in order to reproduce this fact that the black hole horizon keeps decreasing. So and the temperature keeps increasing. What you find is that the sum of the positive Lyapunov exponents, which is called the Kolmogorov-Sinha entropy, that decreases, but the maximal Lyapunov exponent actually increases. Yeah. So which means the temperature increases, whereas the entropy decreases.
Yeah.
So in fact, you need a spectrum then to capture black hole physics in a way.
Yeah, I should also say that the theorem that, so in classical chaos, there's this thing called the Kolmogorov-Sinai entropy, and there's a theorem by a guy called Pessin who proved that this Kolmogorov-Sinai entropy equals the sum of all positive Lyapunov exponents, right? That's what you're referring to. So in quantum chaos, we have absolutely no idea what this even is. So it's a very murky subject. So we don't even know what is the Kolmogorov-Sinai entropy in quantum mechanics. There are two proposals. One is called the Alitzky-Fanes proposal. The other one is called the Kohn-Nierendorfer-Tiering proposal for how to actually compute this for quantum field theory. They're both extremely complicated and they're both wrong. So there is no, I mean, they're wrong because they, for the one or two cases where they were computed, they gave a nonsensical result. You know, at the very least, if you're working with a free theory, it should say that the entropy is 0. So this entropy is wonderful because in classical chaos, it says it's chaotic, it's not chaotic. If it's 0, it's not chaotic. So you compute this quantum field theoretic entropy in a free theory and you get non-zero result. So yeah, so I don't know. I think I've thought about this a lot, about this Kolmogorov-Sinai entropy. I don't know what is the quantum equivalent of this. So I don't really know how to apply this to black hole physics. Maybe there's some equivalent to the sum of Lyapunov exponents. I just don't know. I think it's absolutely fascinating question. And all I can say is I can give a lecture about confusions. I really don't know. I have no resolution to this. The only thing I know is that I think that the Lyapunov exponent will be a continuum as a function of momentum. I think that's kind of, you can see this from this Schenker-Stanford calculation of the Hopf-corrected Lyapunov exponents. For Lyapunov exponents close to the collision of the shocks, far away you get back to this single Lyapunov exponent that shows in pole skipping. Yeah, so I don't know. I mean, this is all fascinating. I cannot really make any precise claims about this. And I'm just confused about this entropy. Yeah, so this is the paper, maybe this is Hanada and...
Hanada, exactly, the paper by Hanada, yeah.
I think that's what you're referring to. Yeah, exactly. It's very interesting stuff.
Well, sorry, we have to now really move on to the next talk.
Okay, thanks very much.
for the beautiful talk again.
Thank you, Anne.
Yeah. So Derek is our next speaker.
Right, I have to somehow disengage this thing.
Disengage.
It's not allowing me to. Sorry.
You got to simply. Yeah. Okay.
Yeah. No, I had your pictures over the stop share. Okay. Thanks. Bye bye.